My name is Saif, and I'm a PhD student in the Department of Chemical Engineering in Carnegie Mellon University. My poster is on optimization of natural gas liquefaction process with detailed design of multi-stream heat exchanger model. Natural gas processing has suddenly become a popular topic in process system engineering community. The natural gas liquefaction process is an energy-intensive process which requires cooling natural gas to cryogenic temperatures using a mixed refrigerant. Studies till now have mainly focused on optimization of the refrigeration cycle with respect to the operating conditions and neglecting the design effects of the multi-stream heat exchanger. In this study, we propose a new discrete model based on fundamental heat equation for design of the multi-stream heat exchanger. Along with, we also propose a trust region strategy which can embed the detailed design inside the process flowsheet model. The natural gas refrigeration cycle can be considered as a mixed refrigerant thermodynamic cycle, where the mixed refrigerant is a mixture of hydrocarbons used to liquefy the natural gas to approximately minus 155 degrees Celsius. The major components which consume the most energy in this flow sheet are the low and high pressure compressors. The objective function for this process flow sheet optimization problem is to minimize pumping costs, mixed refrigerant flow rate cost, and the capital cost associated with the area design of the multi-stream heat exchanger. We imagine this exchanger as a cascade of finite elements. Inside these finite elements, we discretize the heat equation for all the streams using finite difference method. The enthalpies and the stream temperatures are calculated using cubic equation of state, and the liquid and vapor fraction of each of these states undergoing phase change can be calculated using flash calculations. The exchanger area inside each of these elements is then related to the design variables such as number of coils, tube lengths, diameters, thickness, etc. Used to embed these detailed exchanger design models um, uses reduced models and trust region constraint. The trust region constraint is added to ensure that the reduced model is a good approximation of the detailed design model. Along with the trust region constraint, a filter is also used to store set of solutions and model infeasibility and objective values. The filter condition ensures that this model infeasibility and objective function always decreases as the trust region radius is decreased. Under mild assumptions, we can prove that the solution given by this trust region strategy is equal to the optimal solution of the overall design problem. Heat exchanger. A novel discrete model has been introduced to design geometric design variables of spiral wound heat exchanger. Along with that, we also propose a trust region strategy to embed these detailed designs inside the overall flowsheet problem. And this trust region filter is also developed to ensure that the solution to the trust region strategy is equal to the true optimal solution. At last, I would like to acknowledge funding from HIF for this study, and I would be happy to answer any questions directed at this email ID address on the bottom of the slide. Thank you very much.